Hi, Philip. Welcome, everyone, to the last talk of this session before the poster session, I believe.
Yep, I also think so.
Okay, great. So, well, Philip's going to tell us about effects and mitigation of realistic readout noise in quantum approximate optimization algorithms. And go for it. Take it away, Philip.
Hey, thank you for the introduction, and thanks to the organizers for having me here. So I'm Filip. I'm a PhD student at Polish Academy of Sciences, and I'd like to tell you something about readout noise on quantum devices. Before I begin, let me just say that this is the presentation about ongoing project on which I work with Flavio Bakari, who is now in Munich, Zoltan Zimborat from Budapest, and Michał Szmaniec, who happens to be my PhD advisor. Okay, so I divided presentation into two parts. First will be about the readout noise, and the second will be about its effects on the QAOA, the quantum optimization algorithm. So the outline of the first part is as follows. I will start with description of what is our setup, so the classical measurement noise and its mitigation, and then I will tell you what are the problems with it, which are basically a bunch of inefficiencies, which in the course of presentation, I will try to replace with efficient stuff. Okay, so our setup is following. Let's say that we have some quantum measurement device, and we want to estimate probability vector of its outcomes. Okay, so we sample from the device which makes a quantum measurement. So we would like to sample from some probability vector. We would like to estimate it, but due to some noise, our device actually samples from different noisy distribution, okay? So we don't sample from this, but from this. And this new distribution in this model, this classical model, is related to the original one, the ideal one, by some stochastic map. Stochastic meaning that its columns are probability distributions. So why call this noise classical? Well, it turns out that stochastic map acting on a probability distribution has a nice interpretation as classical post-processing. To understand that, let's take a look at the simplest possible example. So we have a single qubit initialized in 0 state. Let's say we measure it in the computational basis, and then we would expect the outcome to be 0, right? And this would be the end of the story if the measurement was ideal. But we have some noise, okay? And you can think about this noise as some process of relabeling of the outcome. So we have some probability of correctly identifying the outcome, but we also have some probability of making a mistake, okay? And if you want to construct a single qubit lambda from that, you simply put the probability in the first column of this matrix, and if you wanted the second column, you would put the another computational basis state. And of course, you can probably clearly see from this, we generalize it for higher number of qubits. You simply put more computational basis states, and you have some more probabilities of relabeling, more probabilities of errors. Okay, right. So this is our setup, and we see that the interpretation that this noise process as classical post-processing might actually point out at a pretty simple way to correct for such noise, okay? Because we can, we can also perform some classical operation on estimated statistics, those noisy ones, and just left multiplied by the inverse of this noise matrix lambda, okay? So this would be the mitigation of the classical noise. So this is our setup, and one can already pose a bunch of reasonable questions at this point. The question one would be, is the classical noise a realistic model? And the answer is yes, at least for transmon qubits. See, for example, the literature I give here, it was already checked. And the second question would be, does such error mitigation works? And basically the answer is the same. It was verified that it works pretty well for small dimensional systems. So what are the problems then with the thing? Well, I will try to answer to this in the next few minutes. Okay, so recall that we are interested in the mitigation of readout noise by estimating some noisy statistics and multiplication by inverse of lambda, okay? But in order to do so, we obviously need to know the lambda, right? So what is the problem with the characterization of lambda? I hope this slide already hints at that. The problem is here. The reconstruction of the generic noise matrix has exponential scaling, right? It is like a very big matrix to reconstruct. So the solution to that is to note that actually real noise probably won't be generic. We can make use of some locality of correlations. So as an example, think about the simplest model, okay? Completely uncorrelated noise, where the global noise matrix lambda on all qubits is just a tensor product of some single qubit small noise matrices. So I think you can agree with me that it has efficient description and it can actually be easily characterized because those are just single qubit matrices. But unfortunately, this model is not very realistic. It was already demonstrated multiple times in various papers, including ours, so it is not the way to go. Then maybe we can figure out some slightly less simple solution. So to still model correlations locally, but do not be too naive, like in this completely uncorrelated noise model. And now I will try to explain you the main ideas of our readout noise model. Okay, let's say that our device have 4 qubits. Okay, those guys, and now the simplest thing you could do is to actually divide your qubits into strongly correlated sets. For example, like imagine that blue qubits here are strongly correlated in terms of readout noise. Hence, we put them in the same cluster. Okay, let's call this cluster. And other qubits are not so strongly correlated, so they are in their own clusters. And now say that each cluster has some corresponding noise matrix acting on it. And so now, one could, in principle, just assume complete lack of correlations between blue cluster, and the other guys. Construct a global noise matrix by tensor product of cluster matrices. Okay, so this would be some idea. However, this notion is a little bit harsh. I would call it binary, because in such a model, we would have a situation in which either qubits are very strongly correlated if they belong to the same cluster, or they are not at all correlated because we make a tensor product. So this motivates introduction of some Mydel correlations possibility. For this, imagine that the noise matrix on each cluster, okay, depends on the state of the neighbors before measurement. So in this example, qubit at the beginning of the arrow affect the noise matrix on the cluster at the end of the arrow. Okay, so for example, the blue cluster is the noise matrix on it is dependent on the state of the green guy, and red as well, and those guys are dependent with each other mildly. So they are each other's neighbors. Okay? And the bottom line here is that characterization of clusters and neighbors can be cheap, provided they are not too big. Okay, so we have now this a little bit more complicated noise model, but maybe it's more realistic since it's more complicated. So how to construct a global noise matrix on that? Well, the expression for the matrix element on the global noise matrix would factorize in such a nice way on the smaller matrices, noise matrices on those clusters, depending on the state of the neighbors. Okay, so those are bit strings saying which state we put inside the device, and here is what we obtained, what result we obtained. So we can. This was an example, and we can write an equation for like generalization for this for more than 4 qubits. And the thing is that if the correlated sets are of bounded size, then the above model has efficient description because it just needs a bunch of small dimensional matrices to calculate the global noise model. Okay, so how to characterize this noise model? So we propose to perform a parallel characterization using a recently introduced quantum overlapping tomography, like modified for this purpose. So to understand briefly how it works, imagine that you are interested in the noise characterization on pairs. Okay, so you for a single pair you would need to implement those circuits to prepare all computational basis states, and you would need to implement a number of circuits which is proportional to the number of pairs. Okay. And the point is that overlapping tomography tells you not to do it separately, but do a lot of stuff on all of the qubits together, and to get as much information as you can. Okay, and in this way you can construct circuits which give you information about the subset, which is logarithmic in the number of qubits and exponential in the size of the subset you are interested in. So the relevant example here, let's say that you want to characterize 15-qubit IBM's device and reconstruct all noise matrices on all 5s of qubits. Okay, so the separate procedure would require like 100,000 circuits, but overlapping tomography allows you to do so like using, for example, 350 or something like this. Okay, so this is pretty efficient. And basically, if you do this characterization, then you can, from pairwise correlations, get the structure of clusters and neighborhoods. And if needed, of course, you can refine the noise model with standard local characterizations. And I just wanted to point out that there is clearly a bunch of other works on the characterization of readout noise, and I encourage you to check them out. As you can see, all of them are from this year, so I hope we are not too late for the party. Okay, so how it looks in the real device. So this is the scheme of IBM's 15-qubit Melbourne device. This is a physical layout of it, meaning that all nearest neighbors are connected by entangling gate. Now, if we perform our procedure, we can see, for example, the following cluster. Those will be some exemplary results. Okay, so we see that actually we discovered strong correlations only in one pair. Okay, so maybe what about the milder correlations, like the neighborhoods I was talking about? So now the picture gets a little bit more messy. As you can see, the qubits actually talk to each other. And the bottom line here is that the structure of those correlations cannot actually be directly inferred from the physical layout of the device, it seems. Okay, so that was the characterization. Now what's about the mitigation? So I told you that the mitigation is to estimate probability vector and multiply it by the inverse of the noise matrix, okay? And I think it already points out what is the problem. So this mitigation requires estimation and of exponentially big probability vectors, right? So I don't give you the solution for that, actually, but instead we do some workaround and we try to focus on problems which are feasible for this mitigation, okay? And what I mean by this, well, the problems which require estimation of multiple marginal probability distributions, okay? So because this is easy task. And for example, estimation of energy of local Hamiltonians, and by local Hamiltonians, I mean the guys which are some local terms, right? Like, for example, the nearest neighbors. Okay, so to approach noise mitigation on marginals then, let's say that we have, again, this 4-qubit device and we want to marginal on those blue qubits, okay? So we take clusters to which the qubits from your marginal belong, okay? So those blue guys, and now we average over the neighbors to obtain average noise matrix, okay? Which we can do from the characterization. So we average this, and by just averaging over all possible states of neighbors and matrix in this cluster, okay? So we obtain something like this, and now we can use its inverse as a correction for that marginal. And basically, this will not perfectly reverse the noise, it's just an approximation, but it should bring us closer to the noiseless distribution. And up to some errors, which we can quantify, and I don't give it here, but it is proportional to the level of correlations between qubits. So the crucial question, does it work in real life? So to check that, we propose the following benchmark. Prepare classical state, which is a ground state of some local Hamiltonian, perform noise mitigation on marginals, estimate energy, and compare, as simple as that, right? So we did it for a number of Hamiltonians, like 90 Hamiltonians, encoding random max2 set with instances with close density 4 on IBM's 15-qubit Melbourne device, okay? And here are the results. What you see is the histogram. The y-axis is the number of Hamiltonians fitting inside a bin, and the x-axis is absolute energy difference per qubit. So we estimated the energy and compare it to the ideal one using absolute difference. Then we divided it by the number of qubits. The green bars correspond to error mitigated estimators, while the red guys correspond to noisy ones. Okay, so as you can see, it seems that method works quite well. That were experimented with 15 qubits, so I think it's pretty nice result. Okay, so to summarize part 1, I told you that there is a problem with exponential scaling of characterization of generic noise matrix, and we can reduce this problem by introducing some noise model which exploits locality of correlations. I told you that the problem with noise mitigation is that it requires estimation and post-processing of exponentially big probability vectors. And then I told you that we can work around this and just for now focus on the problems which are feasible, meaning the ones which require estimation of marginal probability distributions. Okay, and the notable example of such problems which require this is the quantum approximate optimization algorithm, or QAOA. And this is my transition to the part 2. The outline of this part is following. I will briefly say how the QAOA works. We'll tell you about some effects of readout noise on QAOA with some numerical results, and I will briefly describe unrigorously sampling complexity. Okay, so the quantum QAOA is a hybrid quantum classical algorithm developed by Parry, Goldstone, and Gutmann in 2014. And the input to this QAOA is local diagonal Hamiltonian, which encodes you some optimization problem. Okay, some classical optimization problem. And the task for quantum device is to find a ground state energy of this Hamiltonian. And how it goes, the first step is to parameterize your quantum state by some angle theta, which is a parameterization which should be easy to implement. And the second step is to estimate objective Hamiltonian, okay, on this state. Then you call the classical optimizer to update the parameter. You can think about this optimizer as, for example, gradient descent. And then you update those angles, repeat the states, okay, and you basically just repeat until convergence. Okay? So what can go wrong in presence of readout noise? Well, during the optimization stage, this is not surprising. Each estimator will be noisy. This means the wrong energy in each optimization step, right? So in each optimization step, we will have some wrong energy, some noisy energy. And the second thing is that due to this, our optimization can actually land in the wrong regions of parameters. So please note that this is not like necessarily true a priori, because one can imagine a type of noise which does affect the estimators, right? But doesn't change the landscape of energy, like, for example, if it doesn't change the gradient. Okay, so let's take a look at the numerics. So we did some simulations for 8 qubits. We took the readout noise model based on IBM's device, and we performed some tests for the max 2-sat Hamiltonians with close density 4 and a complete graph with random ZZ interactions. Okay. Let me start with the results with the estimators of energy. Okay, so we sample and we estimate the energy. So first, max 2-sat. On this graph, the x-axis shows you so-called number of layers. Okay, you can think about this as an epoch of optimization process. Y-axis shows the energy difference per qubit. So this is the same I used before. I just take estimated and ideal value, calculate absolute difference, and divide it by the number of qubits. And here, each data point is an average over 92 Hamiltonians, okay? Independent runs and different Hamiltonians. So you can see 3 colors on this graph, and the red points correspond to the noisy estimators. The blue dots are noiseless for the reference, and the green dots are the error mitigated ones. Okay, so basically the idea is to compare the green and red ones to the blue guys. Okay, so as you can see, the error mitigation works pretty well for the estimators, and this is for the random ZZ estimators, which also works pretty well, maybe except for the first which is basically the same. Now, what happens about with the expected values? Okay, so by this I mean that instead of looking on estimation of energy, we can look at the parameterized state at any given moment of optimization, and then calculate what is actual expected value of the Hamiltonian on that state. So this will tell us whether the parameters region we landed in is good or not. Okay, so here are the results for max 2-sat. So the plot is exactly the same as before, but here now we have expected values instead of estimator. So you can see that the difference now is much smaller than before. Error mitigation still helps a little bit on average, but the effect is much less dramatic than when we look at the estimate. So this means that the energy landscape was only mildly modified by the noise. Okay, and the similar effect is seen with the random ZZ interactions, where here actually the difference is almost not visible, but basically here we have quite good results, which means that well, error mitigation helps with a little bit faster convergence here. So those are results just for 8 qubits, so one can expect that probably for high-dimensional systems, noise will only get more complicated, which will possibly make the difference, like in this plot, bigger. So those were numerical results about some QAOA, and now very briefly and unrigorously about the sampling complexity, okay, and the particular aspect of it. So basically in QAOA, one simultaneously estimates expected values of multiple local terms of some Hamiltonian, okay, they commute, we can measure them simultaneously. And now we can perform the following observation, okay? So for variety of states, the correlations between long-range marginal states are actually small. So this holds for the states generated by random local quantum circuits, random states, ground states of local Hamiltonians, and also interestingly, states from shallow depth QAOA, okay? From that, it follows that actually most terms, when you treat them as random variables, they behave as uncorrelated variables, okay? And this means that basically the variance of the whole Hamiltonian is more or less the variance of the of all of the terms, the sum of the variance. So what are the consequences? So this will be very unrigorous, but basically the naive additive bound, which you would get for the statistical errors, gives statistical error scaling like the number of Hamiltonian terms, in the sense that we assume that each of those guys like gets the worst error possible, okay? But instead, since the variables are uncorrelated, we will expect something scaling more like square root of n, okay? And I will show you some just some plot with numerics. So basically here you can see here is still absolute energy error, this time not divided by the number of qubits. And here I varied the number of Hamiltonian elements, okay? So again, each data point is average over a number of Hamiltonians. And basically what I want you to look at is that the red points are the additive naive error bound. This is what we would expect from uncorrelated variables, more or less. And this is what actually happens in the numerics, okay? So it seems that it actually works even better than the uncorrelated variables in practice, right? And the short question which is relevant to us is, do noise and error mitigation change the situation? And the short answer is that we have reasons to believe that they do not. And those reasons are that we have some analytics for very simple noise model and numerics for complex noise model. So this is basically the same as before. We still have those errors, but statistical error in absolute energy difference, but now with the error mitigated estimation of Hamiltonians. Okay, right. Okay, so let me go to the summary of the presentation. I told you about the model of classical measurement noise which exploits locality of correlations. I told you how to efficiently characterize this using modified quantum overlapping tomography. I presented you some results of experiment on 15 qubits with successful noise mitigation on those 15 qubits. I told you that QAOA can be affected by readout noise, and that the numerical results suggest that proposed error mitigation strategy can help with reducing them. And finally, I briefly mentioned that in shallow depth QAOA, the local terms behave as uncorrelated variables, and readout noise and its mitigation should not significantly increase sampling complexity in this sense. Okay, so that would be it. Thanks a lot. I'm happy to discuss some questions.
Hi, Filip. Thanks a lot for the great talk. So we are a bit past schedule.
Right. Yes, we started.
Well, it's not really your fault. I mean, like, it's sort of like
I was trying to be
sort of like the fault of people behind.
Yeah, I know how it goes.
So, I guess I have a quick question, and then perhaps the follow-up questions we can take on Slack. So,
of course, yeah.
When you sort of develop these noise models for this particular algorithm on certain specific devices, can you derive some basically sort of like some directions for technological improvements, like stuff that we should work on to make it more likely that we can perform these algorithms reliably or read out their results reliably?
Right. So that's quite a deep question, I would say. And if you ask about, let's say, the hardware solutions, then I would say that absolutely not, in the sense that our noise model, it is very abstract, okay? So we don't care, in a sense, about the dynamics. We try to work on the operators, okay? On the abstract level of quantum mechanics. So this doesn't give us we don't consider in our project some physical reasons for that. As of now, of course, this is a nice future research direction. So in this sense, it doesn't guide it, but also the abstract approach is powerful, because you can, in principle, apply it to the multiple devices, right, independent of the technology used. But on the other hand, you can what you can do is to basically, if you are like some provider of some quantum devices, I would say that the methods like ours would be perfect candidates for stuff which is used for calibration, right? Because if you perform such characterization, then you can learn something about the errors in your device, and it can provide you a feedback to the users. Also, probably it would be super cool to even store the possible correction matrices, not to assuming, of course, that they will be stable in time during the calibration period. So this is also another issue. So I just partially answer your question, but this is a very broad subject. So
sure, yeah, no. Mm-hmm. That's great, thank you. Okay, perfect. So maybe let's leave it at this for today, and we can take any more questions on Slack if there are more. Thanks a lot, Filip.
Thanks a lot. Bye-bye.